Now we're going to look at the exponential function. So we'll start off with a bit of background. What is an exponential function? Let's take a look at an example. Here we have a graph of the function y equals 2 to the power of x. We call this an exponential function because x, which is the input, appears as a power or appears as an exponent. So an exponential function is where your input is a power. So we have a base, in this case the base is 2 to some power, and that power is our input. So we can see from the graph here, if we take an input of 1, our output is 2. If we take an input of 2, our output is 4. And this should make sense if you think about it. If you have x equals 1, if you input 1, well then y will equal 2 to the power 1, which is 2. So that's why our y value is 2. Similarly, if we take our input to be 2, our output y will be 2 to the power of 2, which is 4. And you can see that right here. 2 to the power of, what about 2 to the power of 3? Well, we know that 2 to the power of 3 is 8. So this is a simple example of an exponential function, this particular one, y equals 2 to the power of x. So let's take a look at another example of an exponential function. Here we have the exponential function y equals 3 to the power of x. And if we have an input of 1, we know that 3 to the power of 1, that is 3. If you have an input of 2, 3 squared is 9, and so on. If you have an input of 3, 3 to the power of 3 is 27, and so on and so on and so on. So you can see the exponential function 3 to the power of x here. How about another example? Here we have an exponential function 10 to the power of x. So y is 10 to the power of x. So we can see that 10 to the power of 1 will come out right here at 10. 10 to the power of 1 is 10. That should make sense. What about 10 to the power of 2? 10 to the power of 2 we can see is 100. 10 to the power of 3 you can see is 1,000, and so on and so on. So exponential functions are fairly straightforward concept. Your input is just the power. The base number will be defined and your input will be the exponent or the power. Now, the one that we're most interested in for this video is a particular exponential function y equals e to the power of x. So my base that I'm interested in is the base e. We've looked at the base 2, we've looked at the base 3, we've looked at the base 10, but what I'm really interested in is this base e. So this number e is a mathematical constant roughly equals to 2.718281828, and it's a non-recurring decimal. It is an irrational number discovered by the Swiss mathematician Jacob Bernoulli in the 17th century when he was doing investigations on compound interest. And if I want to be more technical, the strict definition of the number e is the limit as n goes to infinity of 1 plus 1 over n to the power of n. Now, we don't need to worry about this definition right now. We just need to understand that the number e is a naturally occurring limit when we talk about continuous growth. Okay, so what about this function here, e to the power of x? Let's look at this in a little bit more detail. So, we're looking at this exponential function. The exponential function is used when a quantity grows or decays at a rate proportional to its current value. What this means is that if a value is bigger, it will grow faster. Or if the quantity is bigger, it will grow faster. Or if it's smaller, it will decay slower. A simple example is to think of population. If you have a population of 1 million versus a population of 100 million, the population of 100 million will be growing faster than the population of 1 million because if there's a population of 100 million, there is more people around to reproduce, therefore that population is going to grow faster. So it's a natural idea. The exponential function is used when a quantity grows or decays at a rate proportional to its current value. We can use this function for many situations, including growth of bacteria or any population, radiocarbon dating, i.e. telling us how old fossils are, depreciation, or continuously compounding interest. And we've already looked at this. The basic example of the exponential function is written as y equals e to the power of x. So let's look at some properties of this exponential function. We can see the graph of the function here on the left. So the first thing that we need to understand is that e to the power of x, the function will be greater than 0 for every value of x. So you can see that here in the graph. It never drops below 0. And because it's usually used to model quantities, we're not going to have negative quantities. Therefore, this graph is never going to be negative. Either side of the axis, it will never drop below the x-axis. We will never have negative outputs. As x approaches infinity, the exponential e to the power of x approaches infinity very fast. So this is by saying as the input grows, the output grows even faster. And you can see that from the graph. As we go from left to right, the graph is growing really, really fast here. So it's going up faster than it's going to the right. So that's what this property is saying. That as our x values grow, as our inputs get bigger here on the x-axis, the outputs get bigger even faster. And you can see as I zoom out, you can see how quickly this exponential function really starts to grow. Then the next property, as x approaches minus infinity, the exponential function approaches 0. It approaches 0, but it will always be greater than 0. It gets very close to 0, as you can see here. As you go through negative values of x, if we zoom in here, we can see that the exponential function itself gets close to 0, but it never ever actually touches 0. If I condense this down and zoom in a little bit further, you're going to see that. So as we go in here, if we zoom in and zoom in, you can see it gets close to 0, but never ever touches 0. All right, so that is an important concept as well. So as the power of the exponential becomes more and more negative, the exponential itself approaches 0. And the final property here, e to the power of 0 is 1. So if your input is 0, your output is 1. Anything to the power of 0 is 1. So therefore, e to the power of 0 is 1. So before we go any further with the exponential function, we're going to take a look at solving exponential equations. Being able to solve exponential equations is an important skill related to exponential functions. So we can see a lot of exponential equations here, and we just need to understand how to solve these. So let's start off with a straightforward example. We look at the very first one here. E to the power of x equals 10, and we want to solve for x. So we've got e to the power of x equals 10. So how am I going to solve this? Well, what we're going to do, we're trying to solve for a power. So we're going to use logs. And in this case, we're going to use the natural log. By the natural log, I mean log to the base e. That is our natural log, log to the base e. And the reason we will use this is because of our natural log rule. So if we take, for example, log to the base e of e to the power of x. Remembering our log rules, what is this going to be worth? Log to the base e of e to the power of x. So what I can do is I can use my log rules. I can bring this power down in front. So I can rewrite this as x times log to the base e of e. All right. Now, what about this log to the base e of e that we see here? Well, we know that the value of this is 1. Why is it 1? Because we're thinking e to the power of what number will give me e. So if you have log to the base e of e, that's 1. So we're really just with x times 1, which is simply x. So log to the base e of x is equals to this, x times log to the base e of e, which is equals to x times 1, which is x. So moral of the story, log to the base e of e to the power of x is simply equals to x. And that's an important idea that's going to help us solving these exponential equations. One other important idea, log to the base e is often written as ln. ln coming from the Latin for natural log. All right, so if you see ln, that means log to the base e. So if you see log to the base e of x, that's the same thing as the ln of x. Okay, so now that we've examined this, let's go back to our log equation, our exponential equation over here. So we've already seen that log to the base e of x is simply x. So we use that idea to help us solve for the power. So because it's an equation, we have to do the same thing to both sides. So I'm going to get log to the base e of both sides. Or in other words, I'm going to get the ln of both sides. So that's what I do. So I get the ln of e to the power of x is equals to the ln of 10. And we've already seen that ln of e to the power of x is simply x. Okay, so some people like to look at it as the ln and e cancel, but we know what's really going on in the background. We've visited that here on the right hand side. So my next line will simply be x is equals to the ln of 10. And then it's just a case of putting it into your calculator. And our answer, if we stick to 3 decimal places, is x is 2.303. So that was fairly straightforward. In order to solve the exponential equation, in order to solve for the power here, we just got the ln, the natural log of both sides, and that allowed us to solve for x. So let's have a look at another example here. E to the power of 3x is equals to 150. So we've already seen that in order to solve for the power, you're going to get the natural log of both sides. So the ln of e to the power of 3x equals the ln of 150. And we know that the ln of e to the power of 3x is simply 3x is equals to the ln of 150. So if 3x is equals to the natural log of 150, then x is equals to the natural log of 150 divided by 3. And then we just put that into our calculator. And we'll get x is 1.67. Okay, let's have a look at one more example. Let's say I have 4e to the power of 2x is equals to 32. So once again, we know in order to solve for the power, we're going to get the natural log of both sides. But we have to deal with this 4 first of all. In order for our log and our e to cancel here, we need to have the natural log of just e, not the natural log of 4e or the natural log of 5e. So what we want to do here is, first of all, we're going to divide both sides by 4. First of all, so dividing both sides by 4, we'll have e to the power of 2x is equals to 8. And now we can get the natural log of both sides. So the ln of e to the power of 2x is equals to the ln of 8. We know that the ln of e to the power of 2x is simply 2x is equals to the ln of 8. So therefore, x is equals to the ln of 8 divided by 2. And put that into your calculator, and we'll get x is 1.0397 if we go to 4 decimal places. So that is how we solve exponential equations. And as I've already said, solving exponential equations is an important skill in working with exponential functions. So now we look at how to create functions to model real-world situations using this this exponential function idea. So our basic model for the exponential function we're going to use is y equals ae to the rt. You're going to see a lot of this in this video. So we use the basic model y equals ae to the rt to describe many situations where a quantity grows or decays at a rate proportional to its current value. And we've already talked about this. This means that the bigger it is, the faster it grows, or if it's decaying, the smaller the value is, the slower it decays. Okay, so we have, as I said, the basic model y equals ae to the RT. And we've got a couple of parameters and variables here that we have to understand. So E, we know what E is. E is the number 2.718, so on and so on. What's important here, A, the parameter A is going to be the initial value of whatever we're investigating. The initial value when the time is equals to 0, when this model first starts. When the time is equals to 0, whatever the value is at that time, we call this A. Or then, you can see this R is in the power. R is the growth rate or the decay rate. All right, it'll be positive if it's a growth rate. It'll be negative if it's a decay rate. And we'll examine all of these examples anyway. And then T is the time, the independent variable. That would be our input variable T for time and your output variable Y for the value. So how can such a simple setup, how can such a simple function model so many different real-world situations? Well, let's examine that. So here we have a graph of the basic exponential model, y equals ae to the RT. Now in this particular graph right now, a, our initial value, is set at 1, and r, the growth rate, is set at 0.5 or 50%. So let's just examine a first of all. Remember we said a is the initial value. So if we look, a is set at 1 right now, and the initial value right here is 1. When t is 0, the horizontal axis is my t-axis, t for time. The vertical axis is the y-axis, y for the amount at that time. So at time 0, the amount is 1. And that should make sense since our a is set at 1. Now what if we change the value of a? So if we change the value of a, let's say we make a 2, you can see here on the graph how that affects it. Now the graph starts at 2. When t is 0, our value is 2. And same again, if we continue on and set a up as 3, so now a is 3, you can see our initial value, therefore, is 3. So you can see that changing the initial value, changes where it cuts the horizontal axis and rises the graph up and down, basically. So if I change back to 1 now, set our a at 1, we can see that the graph starts at 1. What about the growth rate? So right now the growth rate is set at 0.5 or 50%. So if we change that, let's say I increase it, make it a 0.6 growth rate or a 0.7 growth rate, you can see that it's growing faster. So my a is set at 1 right now, so that hasn't changed. But as I change the growth rate, you can see that the line or the graph increases faster and faster. And then the opposite is true as well. If I decrease the growth rate, you can see that the graph is increasing slower. What if we set the growth rate at 0? So if we set the growth rate at 0, what do you expect to see? Well, if the growth rate is 0, there's no growth. So then you're going to have a perfectly horizontal line. All right, a perfectly horizontal line. That should make sense because our growth rate is set at 0, so we have no growth. And then depending on, let's move our a up to 2 or 3 for a second. So let's say I have a at 3. What if we include a negative growth rate? What about a negative growth rate? Well, we know we call negative growth decay in this case. So a negative growth rate, we're going to call that a decay rate. And as you can see, a negative growth rate or a decay rate means the values are decreasing. And the more extreme we make this negative growth rate, the faster the values are going to decrease, as you can see here. So what I'm trying to illustrate here is that using this exponential function, this ae to the RT, you can model so many different situations for depending on your values of a and r. So for different values of a and r, you can create an equation or a function that models many different situations. Remembering that a is the initial value when t is equals to 0, and r is the growth rate if it's positive, or the decay rate if it's negative. So now that we've looked at all of the background, let's have a look at an example of a typical question here. So we look at this question 2 here first of all. This is a fairly straightforward, very easy introductory question. So €100 investment gains value by continuously compounding at a rate of 4% annually. Create a model in the form V equals AE to the RT, where V is the value of the investment in euros and T is the time in years. And then we've kind of got two questions. How much will the investment be worth after 5 years? And the second question, how long will it take the investment to double? So in order to figure out how much will the investment be worth after 5 years, and in order to figure out how long will it take the investment to double, we need to create the model first of all, or to create the equation or the function that describes this particular situation. So we're dealing with a function of the form V equals AE to the RT, and remembering that A is the initial value and R is the growth or decay rate. So in this particular question, if I read it carefully, it was €100 investment and it was continuously compounding at a rate of 4%. So my initial value is €100 and my growth rate is 4%. So I have both pieces of information I need. So we can take that right here. So we know that our initial value, A, was €100 and our growth rate was 4%. Now 4%, we're going to write that as 0.04. So we express it as a decimal. Now, a lot of people sometimes ask me, why is A 100? You know, how can we assume that the initial value is always A? So let's just take a look back at this question again. So the question was, it was €100 investment that gains value by compounding at 4% annually. So it was €100 investment. So that means when the time was 0, when this thing started off, when T was 0, the value was €100. So we know that we're taking a model of the form V equals AE to the RT. And if I sub in, well, when T is 0, the value is 100. So let's sub those two values into our function here. So the value is 100. So 100 equals AE to the power of R times, and the value is 100 when time is 0. So R times 0. Now you get 100 equals A times, and this is going to be E to the power of 0 basically. And E to the power of 0 is 1, because anything to the power of 0 is 1. So you get 100 equals A, therefore 100 equals A times 1, so 100 is A. So your initial value, or your A in this particular case, is 100. And that's why we can say, like we say here, A is the initial value, because when you sub in your T equals 0, like I did right here, and put your initial value in for V when T is 0, you'll always end up getting whatever the initial value is will equal A. So sometimes we just skip that step and we realize, okay, A is going to be the initial value. So in this case, A is 100. So now that I know that A is 100, and I know my growth rate is 4%, it gave us to us in the question, creating the function is very easy. We've got V equals 100E to the 0.04t. And this is the function that describes a €100 investment continuously compounding at 4%. So what would this look like on our graph? So here we have our V equals AE to the RT, and we have a graph here, and on the horizontal axis we've time in years, and on the vertical axis I have the value, which is in euros. Now the particular function that we're interested in is V equals 100e to the 0.04t. So my A is 100 and my R is 0.04. So we will set our A up at 100 and we will set our R at 0.04. So this is what the function looks like. 100e to the 0.04t, we can see the initial value when t is 0 is set at 100, and it is growing at a rate of 4% continuously every year. So once we have our function figured out, v equals 100e to the 0.04t, we can analyze the rest of the question and try answer the remaining parts. So I was asked, how much will the investment be worth after 5 years? That's what I'm interested in. How much will the investment be worth after 5 years. So we have the function v equals 100e to the 0.04t, and we're interested in figuring out what is the value of v when t is equals to 5. So if we come back to our graph here, we have our graph v equals 100e to the 0.04t, and we're interested in the value of the investment after 5 years. So when t is equals to 5, what is the value of the investment? So this is fairly straightforward. All we have to do is sub 5 in for t as our input in the function. So v equals 100 e to the 0.04 times 5. In other words, v equals 100 e to the 0.2. And all we have to do is put this into our calculator, and you will get v is equals to 122.14. Now remember, this was euros, so it's 122 euros and 14 cents. So we can see here, when t was equals to 5, we put 5 in and our output was 122 euros and 14 cents. So we've answered to part A. How much will the investment be worth after 5 years? We know it would be worth 122 euros and 14 cents. Okay, what about part B? How long will it take the investment to double? So it started off as 100 euros investment. So when it doubles, it would be worth 200 euros. So once again, we go back to our function. V equals 100e to the 0.04t, and the question this time was, how long will it take the investment to double? So we're trying to solve for t. We know that the value must be 200 euros when it has doubled, and we're wondering what will t be when the value is 200 euros. So if we come back to our graph here, we're saying we know the value is 200 euros. How long will that take? What length of time, or what value of t will that be? So in this case, we'll substitute 200 in for v in the function and try solve for t. So what you're looking at right here is an exponential equation. Now, we looked at these a while ago. So remember, to solve exponential equations, we're going to use the natural log. We're going to be getting the ln of both sides. But before we do that, I want to have the exponential on its own with no number multiplying by it. So the first thing I need to do is divide both sides by 100. So I divide both sides by 100, and I will get 2 equals e to the 0.04t. And then I get the natural log of both sides. So the ln of 2 is equal to the ln of e to the 0.04t. And we know that the ln of e to the power of 0.04t is simply just 0.04t. So we have the ln of 2 is equals to 0.04t. Therefore, the ln of 2 divided by 0.04 will equal t. And if we type that into our calculator, we will get t is equals to 17.33 to 2 decimal places. And remember, that was in years. So after 17.33 years, the value of the investment will be worth 200 euros. So on the graph, how long will it take the investment to double? It will take approximately 17.33 years. So this was a fairly straightforward example because we could identify A and also identify R from the question. And we were able to instantly see that the function was going to be v equals 100 e to the 0.04t by reading the words of the questions, right? Those parameters were given to us in the question. Sometimes we have to do a little bit more work to figure out our growth rate especially. So we're going to look at a more challenging example now. So let's look at this example here. In the year 2000, the population of the world was 6.070 billion. In the year 2015, it was 7.3 billion. Use this information to create a model in the form y equals a e to the power of RT, where y represents the population in billions and t is the time in years since the year 2000. Assuming a model of exponential growth, estimate the global population in 2020, 2050. When will the world population reach 10 billion? So before we worry about answering A, B, or C here, we first of all need to create the model. So we know the model will take the form y equals a e to the power of RT. And looking at the question, we have, let's write down this information. In the year 2000, the population was 6.070 billion. So in the year 2000, y representing the population is 6.070. And in the year 2015, the population was 7.3 billion. Okay, so in the year 2015, the population is 7.3. Now these are in billions. That's 6.070 billion at 7.3 billion. All right, so my advice to you is you always want to start at time zero. So the year 2000, when the population is 6.07 billion, that is going to be when t equals 0. And the year 2015, when the population is 7.3 billion, that is going to be when t is equals to 15. So to simplify the situation for ourselves, we should always label the starting year, whatever year we start investigating the process at, as our t0. And then every year on from that, we can figure out. So 2015, when t equals 15. All right, so going back to the function, y equals a e to the RT. My initial value when t equals 0 is 6.07 billion. So therefore, since we know that a is the initial value, we know we can write the function as y equals 6.07 e to the RT. Remember, because our a is our initial value. We've already looked at that. When we have it as y equals a to the RT, a is the initial value. So, and remember, we can work that out. If we're not happy to take that, we can just work it out. We have our y equals a e to the RT, and we know that when t is 0, the population is 6.07 billion. So fill in 6.07 in for y, and fill in t in for 0. Remember, e to the power 0 is 1. So you end up getting 6.07 is equals to a times 1, which is just a. So this is why a is 6.07 in this case. But as I said to you, a will always be the initial value. So the initial value was 6.07. So that is our value for a. Right, but we still haven't figured out what the value for r is. We weren't told what the growth rate was in the question. We have to figure that out. And we have to use this other piece of information to figure out what the growth rate is. So it's telling us that in the year 2015, in other words, when t is 15, the population had reached 7.3 billion. So what growth rate would lead to a population of 7.3 billion after 15 years? Well, that's what we have to figure out. So let's have a look at the graph of this situation. We want to create a function of the format y equals a e to the RT, where our input is time, more specifically the years since the year 2000, how many years have passed since the year 2000, and our output is going to be the population in billions. Okay? So we know our initial value is 6.07. So we know the function y equals 6.07 e to the RT. So that means we know we can set our a at 6.07. So setting our a at 6.07 will look something like this. But we don't know what the growth rate is. We still have to figure out what the growth rate is. And remember, we have this information here that when t is 15, the population will be 7.3 billion. So we're going to use this to help us figure out the growth rate. So when t is 15, we know that the population is 7.3. All right, in the year 2015, the population is 7.3 billion. So that creates another point, the point 15, 7.3. When t is 15, the population is 7.3. So we now have to figure out what growth rate will give us a function that cuts through that point as well. So we have to adjust the growth rate. So we have, after 15 years, a value of 7.3 billion. So we know our value of A is 6.07, but what growth rate will let us go through this point? What growth rate will give us a value of 7.3 when the input is 15? So we'll have to set up some sort of equation to figure this out. So we have our function so far, y equals 6.07 e to the RT, and we know that y will equal 7.3 when t is equals to 15. So we're going to sub 7.3 in for y and 15 in for t and solve for r. So 7.3 equals 6.07 e to the r times 15. So this is another exponential equation, and this time I have to solve for r. So once again, we will be getting the natural log of both sides, but not until we have divided both sides by 6.07. So my first step, dividing both sides by 6.07, 7.3 divided by 6.07 equals e to the power of 15r. Now I can get the natural log of both sides. So the ln of 7.3 over 6.07 equals the ln of e to the power of 15r. So the ln of 7.3 divided by 6.07 equals simply 15r. So if I continue this up here, we can type the ln of 7.3 divided by 6.07 into our calculator, and you will get 0.1845 is equals to 15r. Then dividing both sides by 15, you will get 0.0123 is equals to r. So now we found our growth rate. So once we know our growth rate, we can complete the function, we can complete the model. So the model that best describes this situation is y equals 6.07 e to the power of 0.0123 t. So this model here, or this function, describes the situation where we have a population of 6.07 at time 0, which was the year 2000, and at time 15, after 15 years, we have a population of 7.3 billion. That is described by the function y equals 6.07 e to the power of 0.0123 t, and you can see that function right here. So now that we know that the function is y equals 6.07 e to the power of 0.0123, we can get back to answering some of the questions. So what were the actual questions? So we've created a model. So now, assuming the model of exponential growth to estimate the population, what is the population going to be in the year 2020? In other words, what will the population be when t is equals to 20? Now this is fairly straightforward. We just have to fill t equals 20 into our function. So we will get y equals 6.07 e to the power 0.0123 times 20. This is the part A. And we can just type this into our calculator, and we will get y is equals to 7.76. And remember, this is in billions, so 7.76 billion will be the predicted population in the year 2020 based on this function. Looking at part B of the question, estimate the population in 2050. So in other words, what will the value of y be when t is equals to 50? So this is fairly straightforward. Similar idea. We have the function y equals 6.07 e to the 0.0123, and we want to know what is y when t is equals to 50. So once again, this is just a case of filling in 50 in instead of t. So 6.07 e to the 0.0123 times 50. And once again, you can type that into your calculator and you will get y is equals to 11.23. And remember, once again, that is in billions. So that is 11.23 billion. So that is our answer to part B. Okay, what about the part C here? When will the world population reach 10 billion? So in that case, we know that y is going to be 10 for 10 billion, and we have to solve for t this time. We don't know what t is. So y is going to be 10. So taking our function, we have our function once again, y equals 6.07 e to the power of 0.0123t. And this time we know that y is going to be 10 and we have to solve for t. So we sub 10 in for y. So 10 is equals to 6.07 e to the power of 0.0123t. So this is a situation where we're trying to solve for the power of the exponential. So we're going to get the natural log of both sides. But before we do that, we'll divide both sides by 6.07. So 10 over 6.07 equals e to the power of 0.0123t. Then we get the natural log of both sides. So the ln of 10 divided by 6.07 equals the ln of e to the power of 0.0123t. So moving along here, the ln of 10 divided by 6.07 equals, and we know that this right hand side just becomes 0.0123t. Continuing this on, we can type the ln of 10 divided by 6.07 into our calculator, and we will get 0.499226 is equals to 0.0123t. So then 0.499226 divided by 0.0123 will equal to t. And then typing this into our calculator, we will get 40.59 if we round to two decimal places is equals to t. So it will take 40.59 years for the population to reach 10 billion. That's 40.59 years after the start of the year 2000. So if we look back at the question, when will the world population reach 10 billion? The population will be 10 when t equals 40.59. And if you want to be more specific, during the year, sometime during the year 2040, we predict the population to hit 10 billion. So that is our detailed introduction into the exponential function. The best thing for you guys to do is just to practice these questions to get better. You can check your solutions online. And for access to questions, solutions, graded quizzes and more, visit www.limmymaths.com.